Hello everyone, welcome back to another kinetic tutoring episode. Today we're looking at this AP practice problem. So let's just get straight into it. The prompt reads, a block of mass m and 2m are connected by a light string and placed on a frictionless inclined plane that makes an angle theta with the horizontal as shown in figure 1 above. Another light string connecting the block of mass m to a hanging sphere of mass big M passes over a pulley of negligible mass and negligible friction. The entire system is initially at rest and in equilibrium. On the dots below that represent the block of mass M and the sphere of mass big M, draw and label the forces, not components, that act on each of the objects shown. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So guys, let's take a look at this block M here. We can see that obviously there's going to be a tension going downwards and a tension upwards, so let's draw those two. This is T2, this is T1. On top of that, we're going to have the gravitational force acting on the ball, and finally we have the normal force that is exerted by the floor onto the ball, and that's going to be perpendicular to the slope. Now over here we have the ball of mass big M. It's going to have gravity affecting it, force of gravity once again, and it's going to have T2 affecting it over here. And those are the only two forces that are acting on the ball of mass big M. Alright, let's go to part B. Derive expressions for the magnitude of each of the following. If you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figures in part A. Alright guys, so basically the reason that the question makes sure to state this is so you do not draw the components on this free body diagram. The AP graders do not want to see this on your test, and so if you want to add your components, you're going to have to draw a separate free body diagram, one that is not here. So we're going to want to find the magnitude of the force T2 exerted on the block of mass M by the string. So let's set up our force equations. Here we know that T2 is on the x-axis of this plane, so let's take a look at our F net x. We know that the system is in equilibrium, so the net force is 0, and let's take a look at the forces acting on it in the horizontal direction. We'll say that upwards is positive, so we'll have T2 going upwards. We have T1 going downwards, so we're going to have T2 minus T1, and we can't forget about the gravitational force of the block itself. It's going straight down, and if we draw the components, we're going to have the horizontal component and the vertical component. Sorry, let me draw that a little bit better for you guys. It's going to look something more like this. The horizontal component is going to be its sine theta of the angle here. So we'll have the gravitational force, which is going to be mg sine theta, and that's also going to be negative because gravity is going to be dragging it downwards. Now, since we know that 0 is T2 minus T1 minus mg sine theta, we can move these two over to the other side and say that T2 is equal to T1 plus mg sine theta. And from here, our final step is to find a value for T1 in terms of our, the values that we were given. So let's take a look at this block right here. So let's draw a free body diagram for the block of mass 2m. Here we go. We're going to have T1 acting upwards. We're going to have the gravitational force going straight down, and we're going to have the normal force once again. Now in this case we want to solve for T1, so we're going to look at the horizontal forces. Here the T1 is going to be equal to the only other horizontal force, which is the horizontal component of gravity, which is mg sine theta, but keep in mind that since there's a 2m here, it's going to be 2 mg sine theta. Alright, so let's plug this into our equation here. 2 mg sine theta plus mg sine theta is going to give us 3 mg sine theta. So we'll find that our T2 has a value of 3 mg sine theta. Let's erase this so we have some more room to write. I'm going to write our answer here. Alright, the mass m for which the system can remain in equilibrium. Express your answer in terms of m, theta, and physical constants as appropriate. Alright guys, so here we have T2 is equal to 3 mg sine theta. But if we take a look at our equation over here, we can see that our T2 is also balancing out the gravitational force of this ball here. It's just going to be mg is equal to T2. So as we can see, we can combine these equations to get mg is equal to 3 mg sine theta. Keep in mind that you need to differentiate this big M and this little m. From here, our final step is just to get rid of this g, and we'll get 3m sine theta is the mass of the big ball. Now, let's take a look at our part C. It asks, now suppose the mass m is large enough to descend and that the sphere reaches the floor before the blocks reach the pulley. Answer the following for the moment immediately after the sphere reaches the floor. Alright guys, we're going to move on to the next page. So here are the questions that we are answering. Does the tension T1 increase, decrease to a non-zero value, decrease to 0, or stay the same? So guys, let's draw out our two systems, our before and after. Here we have our before when the ball is in the air, 2 blocks, boom, and then ball slides down, reaches the ground. These blocks have not reached the pulley yet, which means they're still sliding up the surface. And yeah, let's answer these 3 questions with this knowledge. So we know that these blocks are still shooting up the incline because the ball reaches the ground before these reach the pulley. And since they are shooting up the incline, the tension is going to decrease to 0, because if you imagine the blocks sliding up the incline, the string is not going to be taut. The blocks are just going to be sliding with the loose spring. When the blocks slide back down, then there's going to be a tension that is going to be restored. But for the moment immediately after, our tension is going to decrease to 0. Is the velocity of the block up the ramp, down the ramp, or 0? As we just discussed, the blocks are sliding because they have not yet reached the pulley. So it's going to be going up the ramp. And here, number 3, is the acceleration of the block of mass m up the ramp, down the ramp, or 0. Guys, obviously the only acceleration that is acting on the block is gravitational acceleration, which is always pointed down. So our answer here is going to be down the ramp. Now let's take a look at part D. Consider the initial setup in figure 1. Now suppose the surface of the incline is rough and the coefficient of static friction between the blocks and the inclined plane is mu. Derive an expression for the minimum value of m that will keep the blocks from moving down the incline. Express your answer in terms of m, mu static, theta, and fundamental constants as appropriate. Alright guys, so let's take a look at this problem. For these problems, as you may have noticed in the previous problem, if you just approach this problem thinking these two blocks or just one block, you will arrive at the same answer, because this block was 2 mg, this block was mg, and they both, meaning that the gravitational force of both of them combined is going to be 3 mg sine theta. So for our convenience, we're just going to be considering this whole system to just be one object with a mass of 3m. Alright guys, so we know that we're gonna have, let's draw a free body diagram for this block of mass 3m. It's gonna be the gravitational force going downwards, normal force, there's going to be a value T2, which we know is equal to mg, big mg that is, and we also have a force of friction that is being introduced. The question asks, derive an expression for the minimum possible value that keeps the block from moving down the incline. So if we're trying to prevent the block from moving down the incline, the friction is also going to be going upwards in the same direction as tension. So we'll have tension T2 plus friction. So guys, let's find our value here. So we know that friction is simply mu normal. We're told our mu, we're just going to write it as mu, so let's find an expression for our normal force. You know that our normal force is being counteracted by the vertical component of gravity, which is mg cosine theta. So our frictional force can be written as mu mg cosine theta. But keep in mind that when we're talking about m, we're talking about the mass of the entire system, which is 3 little m. So our frictional force is 3 mu little m g cosine theta. Our T2 is going to be equal to big mg. So we'll have 3 mu mg cos theta plus big mg, and then on the other side we have the gravitational force, which is dragging it in the other direction, the horizontal component, which we have discovered is mg sine theta. In this case we're talking about this block of mass 3m, so we'll have 3 mg sine theta. Alright guys, make sure to get this equation down because I'm going to erase this really quick so we have more space. Let me rewrite it at the top. 3 mg sine theta is equal to 3 mu mg cos theta plus big mg. And now it's asking for us to find the minimum value of m, meaning that we want to separate everything from this big M. We'll subtract 3 mu mg cosine theta from both sides. Get 3 mg sine theta minus 3 mu mg cosine theta is equal to mg. As you can see here, there's a common factor of g that can be canceled out. 3m, we'll put this 3m outside our parentheses, sine theta minus mu cos theta, and that will be our value of m. So here you guys have it. That is our answer for part D. And now let's take a look at E. The string connecting block M and the sphere of mass M breaks, and the block begins to move from rest down the incline. The lower block starts a distance d from the bottom of the incline, as shown in figure 1. The coefficient of kinetic friction between the blocks and the inclined plane is mu k. Derive an expression for the speed of the blocks when the lower block reaches the bottom of the incline. Express your answer in terms of m, d, mu k, theta, and fundamental constants as appropriate. Alright guys, so for this problem, we're only really going to have to take into account the block that is closer to the bottom, because as you may remember, that is the heavier block, so it is going to be accelerating faster, and it's just going to be dragging along the lighter block, and therefore the lighter block is going to be going the same speed as it. And the way we're going to solve this is using conservation of energy. So here we have an incline. We're just going to put the one block that we're considering over here. We know that it's a distance d away from the bottom, and we want to find the velocity it's going to have at the bottom over here. So at the beginning it has a potential energy, so let's write our potential energy equation. We know that's equal to mgh, and at the end it's going to all be transferred to kinetic energy, which we know the equation for that is 1/2 mv squared, except for the energy lost to friction. So we have to include work in here, and we know that our formula for work is force times distance, and we're talking about the frictional force in this case. And also, guys, make sure to remember that the m we're talking about here is the block of mass 2m, so let me write 2m here. And our next step is going to be to plug in our frictional force that is acting on the block. We've discovered from our previous problems that our frictional force is going to be 2 mu mg cosine theta times d. And then here we can cancel out this 2 and 1/2. We'll just get plus mv squared, and that'll be equal to 2 mgh. From here we can cancel out our m's, and we're trying to solve for velocity here, so we're going to subtract this from both sides. We'll get v squared is equal to 2gh minus 2 mu g cosine theta times d. And our final step here is going to be to write h in terms of d. Here we know that h is here and d is here, so using our trig identities, this is the opposite angle, so h will be, so this angle here will be sine h over d, so h is equal to d sine theta. So our v squared, let me erase this all real quick. Our v squared will be equal to 2g d sine theta minus 2 mu g cosine theta d. From here, our final step, or sorry, our second to final step is going to be to factor out the common factors that we have here. V squared, we have a 2, a g, and a d, 2gd, and then inside our parentheses we have sine theta minus mu cosine theta. And now our final step is going to be to square both, or take the square root of both sides rather, in order to get our final value for velocity. And here you have it. You'll get square root of 2gd times sine theta minus mu cosine theta. Now let's move on to the next page. Or actually, I do believe that's it. Sorry for the confusion, you guys. That is the end of the problem. I hope this tutorial has helped you. If there's any other points of confusion, make sure to leave a comment in the comment section down below, and I will try my best to address your comments. And yeah, that's all. Make sure to tune in later for more kinetic tutoring videos.